Welcome to Section 5. Now that you've seen how we built the LED class, it's your turn to take the lead. We are going to apply the exact same professional workflow to create PushButton class. This will handle everything from basic reading to advanced features like internal pull-ups and debouncing. Buttons might seem simple, but handling them correctly involves managing states, pull-up resistors, and electrical noise. By encapsulating this into a class, we can create multiple button objects that handle their own complexity, leaving our main logic clean and readable. Our journey will follow the same professional structure we learned before. We'll start with the header interface, move to the implementation, and then add layers of abstraction to solve real-world hardware issues like contact bounds. This is where OOP really starts to show its power. Throughout the section, I encourage you to pause and try to write the code yourself before I reveal the solution. This is your turn to think like an object-oriented programmer. We'll use the circuit we just built, focusing on the buttons connected to pins 2 and 3. Ready to get started. In the next lecture, 05.02, we will begin by defining our PushButton interface in the header file. See you there. It's time to draft the blueprint for our PushButton class. Just like we did with the LED, we start with the header file. This file will define the interface, letting the rest of our program know what a PushButton object is and what it can do, without worrying about the internal wiring just yet. We start by setting up our header guards using the if and def and define directives. This ensures our library doesn't get included multiple times by mistake. We also include Arduino.h, so we have access to standard types like byte and functions like digital read. Inside the class, we define our private attribute, the pin number. In the public section, we create the construct prototype which takes a pin as an argument. We also add a method called read that will return the current state of the button. This is the simplest version of our interface. Looking at this UML diagram, you can see the clear separation. The pin is hidden away, while the constructor and the read method are available for the world to use. This clean interface is what makes our main program easy to manage. The interface is ready. Now let's make it actually work. In the next lecture, 05.03, we will create the CPP file and implement the logic for our PushButton class. See you there. Interface defined, now let's build the implementation. In this lecture, we will create the .cpp file for our PushButton class. We'll write the logic that tells the Arduino how to initialize a pin and how to actually read the electrical state of the button. We start our PushButton.cpp file by including the header file we just created. This links our implementation to our blueprint. Remember to use double quotes because this file is part of our local project. Next, we implement the constructor. We use PushButton : PushButton to tell the compiler this function belongs to our class. Inside, we store the pin number and set the pin mode to input. This ensures the hardware is ready the moment we create the object. Finally, we implement the read method. It returns a byte. which is the result of the digital read function on our private pin. This encapsulates the standard Arduino function inside our object-oriented structure. Now, the user of the class doesn't even need to remember which pin the button is on. The logic is simple but effective. By separating these into a source file, we keep our project modular. If we ever need to change how we read a button, for example, if we move to a different hardware platform, we only need to update this one file. We've built the engine, now let's take it for a test drive. In the next lecture, 05.04, we will create our first PushButton object and use it to read a button state in a real program. See you there. The blueprint is ready, and the logic is written. Now, it's time to bring our object to life. In this lecture, we will instantiate PushButton object in our main sketch and use it to read the physical state of the button on our breadboard. In our main INO file, we first include our PushButton header. Then, we create an instance of our class. We'll call it myButton and connect it to pin 2. Remember, the constructor we wrote earlier handles the pin mode set for us automatically. Now, in the loop, we call the read method of our object. We don't need to pass the pin number anymore because the object already knows it. We'll store the result in a variable and print it to the serial monitor. This is the beauty of encapsulation. The main loop stays clean. When you run this, you might notice the values are a bit unstable if you aren't using an external resistor. That's because the pin is currently floating. This leads us to our next big challenge: handling different resistor configurations inside our class. We have a working object, but it's not very robust yet. In the next lecture, 05.05, we will upgrade our class to handle internal pull-up and pull-down resistors, making our hardware setup much simpler. See you there. In our previous lecture, we noticed that our floating pin can cause unpredictable readings. To fix this, we usually need resistors. But did you know the Arduino has internal resistors we can control with code? In this lecture, we will upgrade our PushButton class to support different resistor modes, making our hardware setup cleaner and more reliable. When we use a pull-up resistor, the pin is connected to 5V by default, reading high. When the button is pressed, it connects to ground, reading LOW. Our class needs to know which mode we are using, so it can initialize the pin correctly. We will update our constructor to accept a second parameter, the mode. We'll use the standard Arduino constants like input or input pull-up. We also add a private variable to store this mode for later use. In the CPP file, we update the constructor to apply the specific mode to the pin mode function. Now, if you pass input pull-up, the Arduino activates its internal resistor automatically. This removes the need for external resistors on your breadboard, simplifying your circuit significantly. By handling this inside the class, your main code doesn't have to worry about the wiring configuration. You just tell the object how it's connected, and it takes care of the rest. This makes your code much more portable across different hardware setups. Our button is now electrically stable, but reading high and LOW is still a bit low level. In the next lecture, 05-06, we will add more abstraction to ask our button a simple question. Are you pressed? See you there. Right now, our class returns high or LOW. But as a developer, you don't really care about the voltage. You care about the action. Is the button pressed or not? In this lecture, we will add a layer of abstraction that translates these electrical signals into a simple true or false answer, regardless of whether you are using pull-up or pull-down logic. Abstraction means hiding the messy details. If we use input pull-up, a pressed button actually reads low. That's confusing to read in a main program. We want a method that simply returns true when the button is pushed, handling that inversion internally. We add a new public method called isPressed. It returns a Boolean. This is the only method the user will need to call most of the time. Notice how our interface is becoming more human-readable and less about electronic pins. In the implementation, we check the mode. If the mode is input pull-up, we return true. If the reading is LOW. If it's a standard input, we return true if the reading is high. This internal logic ensures that isPressed always means exactly what it says. Look how much cleaner our loop becomes. No more comparing against high or low. We just ask the button if it's pressed. This is professional-grade code that is easy to read, easy to debug, and easy to maintain. Our logic is now human-friendly. However, mechanical buttons have a hidden floor call bounds that can trigger our isPressed method multiple times in a millisecond. In the next lecture, 05-07, we will solve this by adding debouncing directly inside our class. See you there.
Welcome back.
While our push button works, hardware buttons have a physical floor call bouncing. When you press them, the metal contacts bounce rapidly, causing the Arduino to see multiple presses in many milliseconds. Today, we will fix this by implementing a debounce mechanism directly inside our class. In the header file, we add 4 new private members. About the delay, this is the debounce time. The purpose is that when you press a mechanical button, the internal metal contacts don't close perfectly. They bounce or vibrate, creating a rapid sequence of high, low signals for many milliseconds. About the state, this stores the last stable logic state of the button. Purpose, it serves as a reference to compare against the instantaneous value from digital read. If the current reading differs from state, it means a potential change has occurred. Next is ignore until. This is the LARCAP timestamp. Purpose, it records the exact point in time when the program is allowed to start caring about button state changes again. Finally, underscore has changed. This is a status flag. Purpose, it marks that the button state has just flipped from high to low or vice versa. And in this class we have a new method called hasChanged. In the constructor, we initialize these values. Delay equals 100, means sets the default debounce delay interval. A value of 100 milliseconds is quite conservative and very safe to stabilize our signal. State equals blah blah. This line is crucial for defining the idle state rest state of the button. If using input pull-up, the microcontroller uses an internal pull-up resistor. so the pin sits at high when the button is not pressed. If using input typically with an external pull down, the pin sits at low when at rest. Ignore until equals 0 initializes the logout timestamp to 0. This ensures that as soon as the program starts running, the button is ready to be read immediately without waiting for any pre-existing delay periods. Underscore has changed equals false sets the change flag to its default no change yet state. About if ignore until is greater than millis. If the current time millis is still less than the ignore until timestamp, a function skips the logic below. This means that while the button is physically vibrating bouncing, the microcontroller ignores the pin, effectively filtering out the noise about else if digital read pin different from state. Once the silent has passed, the function checks if the actual physical value on the pin digital read differs from the last stable state. If they are the same, do nothing. If they are different, that means a valid press or release event has just been detected. When a change is detected, 3 things happen. Ignore until equals millis plus delay. It sets a new logout timestamp for the future, the next 100 milliseconds. During this time, any subsequent mechanical vibrations will be ignored. State equals not state. It toggles the current state from high to low or vice versa to record the new stable condition. Underscore has changed equals true. It flags that a change has occurred. Note, the condition statement, maybe ignore until greater than millis, will work incorrectly, because maybe millis will come back to 0 in the future. We also implement has changed. This method returns true only once per state change. After it's called, it resets the internal flag to false. Constant boolean pressed equals mode is equals to input pull up question mark low colon high. This line makes our code flexible. If you use input pull up, the button is wired to ground. So when pressed, the pin receives a low signal. If you use input with an external pull down resistor, when pressed, the pin receives a high signal. The constant pressed automatically adapts to your hardware configuration. In the next lecture, 05.08, we will combine our LED and button objects to create a responsive system. See you there. In this lecture, we are going to see the real power of object-oriented programming. We have our LED class and our PushButton class. Now, we will combine them to work with multiple objects simultaneously. This is where your code starts to look less like a script and more like a professional system. First, we include both header files. Then, we create 2 LED objects on pins 12 and 10. And 2 PushButton objects on pins 2 and 3. Notice how clean the global scope is. We aren't defining pins or states manually, we are just creating objects. In the loop, the logic becomes incredibly readable. We tell button 1 to check its state, and if it is pressed, we tell the red LED to toggle. We do the same for button 2 and the green LED. Because each object handles its own debouncing and hardware pins, they don't interfere with each other. Imagine doing this the procedural way with global variables, complex if statements. Here, if you want a third LED and a third button, you just add 2 more lines of code. Your main program structure never gets more complicated, no matter how many components you add. Congratulations! You have successfully built and combined your own classes. But we can take this even further. Coming up in lecture 06.01, we'll introduce the LED blinker class, where we use a class inside another class. See you there.